Hi, let's look at an interesting probability problem. This one's called the Monty Hall Problem. So this one's from a TV game show in which a contestant has to choose one out of three doors, and each of these three doors has an object hidden behind it, and one of the three doors has a prize behind it. In this case, this is a car in door C. And as you can see, the other two doors have an object of little value hidden behind them. And the objective of the user is to pick the door that has the car in it. So in round one, the user has to pick one out of the three doors, and after that the game show host opens one of the two remaining doors and reveals that it has a goat in it. So for example, if the user had initially picked the door that had the car in random, the game show host has the option to choose between either door A or door B to open it and reveal that it has a goat behind it. So now the game show host gives two choices for the user in round two. So the user can either stay and double down on the door that he had initially chosen, or he could change his mind and move over to the other door. So in this case, as you can see, if he chooses to move over to door A, he would switch to the wrong door and lose the prize, and vice versa if he had initially chosen door A, and if he chose to switch to the other door, he'd win the prize. So now the problem here is to show whether or not switching to a different door changes the probability that the user can win the prize. So round two is a stay or switch. So this Monty Hall problem is actually a very famous paradox because there are two different types of reasoning that you can give by following two different trains of thoughts, which will take you to two totally different conclusions. So we'll look at the correct answer here, and we'll also see why the other train of thought leads you to the wrong answer. So let's look at all the possibilities here. So let's draw this table. So this is round one. And this is the reveal. And this is round two. And this is the total probability. Okay, so to begin with, we have to assume that there are three different types of doors here. So the door that has the prize can be called as C, because the prize is a car, and the doors that have the goats can be called as G1 and G2, which correspond to goat 1 and goat 2. So let's look at all the possibilities here and see what's going on. So in round 1, if the user chooses to open the correct door, which is C, the game show host can either reveal G1 or G2. So let's look at the case in which the game show host chooses to reveal the goat behind door G1. And in round 2, the user can either stick with the option that he already chose, or he could switch to a different door. So same way, we have two other options in which the contestant initially picked the correct door, but the game show host opened G2 instead, because the game show host has the option of choosing one of the two remaining doors, both of which have a goat in it. So we have two other options in which the contestant initially picked the correct door, and the host opens the door G2. So now if the contestant chooses to stay with the option that he already chose, he is at C, and if he decides to switch, he's at G1. And same way, the contestant could have chosen G1 to begin with. So in this case, the two remaining doors are C and G2. Obviously, the game show host cannot open the door C, which has the car in it. Or if I had forgotten to mention this before, the contestant the game show host can only open a door that has a goat behind it. He cannot open the door that has a car behind it. So in this case, the contestant has opened the first door that has a goat behind it, so the game show host has to open G2 to reveal the goat behind it. And if the contestant decides to stay with this option, he stays with G1, and in the case in which he chooses to switch, he moves to C. And we have the corresponding case in which the user chooses G2 at first, and the game show host has only one option in which he has to open G1, and the contestant stays with G2, or he switches to C. So we now see that we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities here. And out of the 8 possibilities, we see that 1, 2, 3, 4, which lead to the contestant winning the prize. So it does appear that we have 4 out of 8 options which result in a win, and the remaining 4 out of 8 result in a loss, which again shows that this is an even 1 by 2 versus 1 by 2, which is a 50-50 chance of winning or losing, irrespective of whether the user decides to switch or to stay with the original choice. But this is not what's exactly happening here, because we need to look at the actual probabilities here. So as you can see, the probability of choosing the right door at first is actually 1 out of 3, and the probability of choosing the wrong door, which is 2 out of the 3 doors, is actually 2 out of 3. So and we'll also see what happens if the user switches or if he chooses to stay with the same option. So I'll color code this, and I'll strike the lines in which the user has chosen to stay with this option using a green line, and I'll use a red line to show the cases in which the user has chosen to swap. So if you look at it, the total number of cases in which the user stays and wins are 4, and 2 out of these cases result in a win. So if you look at this, this is a win, this is a loss, this is a win, this is a loss, loss, win, loss, win. So the probability of this win is actually 1 by 3 times 1 by 4, which is 1 out of 12. Okay, so now if we look at both the cases in round 1, we can see that if the user had initially chosen the right door, which has a probability of 1 by 3, then if the user switches in round 2 to a different door, then he always loses, because the color code for the switch is the red, and that always results in a G. And so this means that there is 1 by 3 probability, 1 by 3 of the occurrences will result in a loss if the user always switches. On the other hand, if the user had initially picked the wrong door, the switches always result in a win, and staying with the original selection always results in a loss. So if the user always switches, there is 1 by 3 chance of a loss and a 2 by 3 chance of a win. So which shows that the correct strategy for this game is to always switch. And remember that in an independent in an independent attempt at this game, this strategy is not going to guarantee that you'll win this game. But if you play the game enough number of times, the results should converge in a way that shows that the number of times that you win would be twice as much the number of times that you lose if you always switch. So now when we go back to the paradox, the reason that this looks like there is an even chance of winning or losing, irrespective of whether you switch or stay with the same choice, is because we assign equal weights to these two cases instead of assigning third and two-thirds weightages, because the likelihood of you choosing one of these two routes is different, which is exactly in the ratio of 1:2. So I hope you enjoyed this video, and please leave a comment if you have any suggestions or any questions regarding this problem, and I'll see you later with another interesting problem. Thank you.